Okay, so this is the third lecture for Chapter 3, Lecture 3, Part 3. In this lecture, we're going to talk about trigonometric functions of angles. So, Lecture 3, Part 3. Trigonometric functions of angles. All right, so in this case, in the figures, we have a drawing of an angle theta, and theta, the angle theta actually forms a right triangle where this point P, which is I guess the terminal point for terminal number R, for instance, and the R is the radius of the circle. So in this case, here you have theta being in the first quadrant, and then theta measure, say, between 180 and 90 degrees in this second illustration. And then in the third illustration shown here, we have similar triangles shown, where the point P and the point P prime, this is red P prime, and the coordinates of P prime are X prime, Y prime. Okay, and Q prime is the point on the x-axis, which is where a perpendicular drop from P prime intersects the x-axis. So we're going to use these figures to derive some quantitative relationships. And so we'll have the following results. So let theta be an angle. In standard position, as shown in these illustrations, by the way, and let P, the point P with coordinates x, y, be a point on the terminal side. Okay, so if we define a radius, R, which is equal to the square root, let me draw it, hello, the square root of the abscissa squared plus the ordinate squared, okay, where x and y, of course, are the coordinates of the point P. So if we define R as this quantity, and so then R is the distance from the origin to the point P, the point P x, y. All right. Okay, and if that's the case, then we can reestablish our trigonometric functions as follows. So we'll have the following. Do they have them not? They don't have them set up here, do they? Okay, so we'll have sine of theta is equal to y over r. The abscissa over the hypotenuse. Okay, and then we'll have let's see if I can paste. I can't paste. All right, so then we'll have cosine of theta equal to x over r, equals to x over r, the abscissa over the radius. Then we'll have the cosecant of theta cosecant of theta is just 1 over the sine of theta. Which of course is equal to y, r over y, r over y. Or of course, where y is not 0. So that would be r over y. And then we have, then we'll have the secant of theta. I have x right here. Actually, that should be theta, right? That should be theta. Then the secant of theta is equal to 1 over the cosine of theta. Which of course is equal to r over x, where x is not 0. Okay, and then the tangent of theta Okay, so the tangent of theta which is equal to y over x. So that's equal to y over x. And then the cotangent of theta is x over y. So memorize these 6 functions and understand what they mean geometrically. All right, so the 6 trigonometric functions. Here they are. Okay, so there are all 6 of them right there. So those 6 equations you have to memorize. Okay, so we have what are called quadrantal angles. The definition of quadrantal angles. So quadrantal angles are angles that are coterminal with the coordinate axes. Okay, so we have that result. Then we can build a table. Let's see if I can insert a table. It'll let me. Insert table. So 1, 2, 3 columns. 5 rows. Okay, so let's work with this table. Let's build a table of information. So, oops. So the first column we'll consider. What we're going to do is we're going to analyze the signs of each of these 6 functions in the different quadrants. So we have already discussed what quadrants 1, 2, 3, and 4 are. So quadrant 1, quadrant 2, quadrant 3, in quadrant 4. All right, so here are the 4 quadrants. And so which functions produce positive outputs? So positive outputs. So in quadrant 1, all the functions generate positive outputs. In quadrant 2, the only functions that produce positive outputs are the ones where y is, well, first of all, r is always positive. Okay, r is always positive. So in quadrant 2, the functions that generate positive outputs will be the ones where y is positive. So this would be sine and cosecant. Okay, both of those functions will yield positive outputs in the second quadrant. In the third quadrant, the only functions that yield positive outputs would be the tangent function, let's try it again. Working with tables is not having too much luck with tables, am I? It will be the tangent function and the cotangent function. Both of those will yield positive outputs in the third quadrant. And why is that? Because in the third quadrant, both x and y are negative, and the tangent is y over x, so the division of 2 negative numbers is positive. Cotangent is x over y, and the division of 2 negative numbers is positive. And then finally, in the fourth quadrant, the functions which yield positive outputs would be the cosine function, because the cosine is x over r, and x is positive in the fourth quadrant, and the secant function, which is 1 over the cosine function. So those would be positive outputs. Okay, so then for negative outputs, all right, so in quadrant 1, none of the functions yield a negative output. Okay, and in quadrant 2, where x is negative in quadrant 2, so that means that cosine, which is x over r, will be negative, and then its reciprocal will be negative, secant, and then the tangent function, which is a positive over a negative quantity, and then the cotangent, which is x over y, and that'll be negative. So those 4 functions will be negative in quadrant 2. In quadrant 3, if it's not tangent or cotangent, the other functions will be negative. Okay, so sine, cosine, secant, and cosecant will all be negative in quadrant 3. And in quadrant 4, the remaining 4 functions will be, the remaining 4 functions that weren't listed in the positive outputs will be negative. So sine, cosecant, tangent, and cotangent will be negative in the fourth quadrant. Okay, so that's how we orient ourselves. So let's see here. Let's look at an illustration on the next page. Okay, so in this illustration, here I give some examples of a 30-degree angle and a 390-degree angle being coterminal. That's what's shown in the first illustration. And then in the second illustration, I show you the orientation of 45-degree angle and 135-degree angle. So you can see the terminal point for the 135-degree angle. So the point it's on the terminating side of the 135-degree angle, the coordinates of the point would be negative x, y. So it's a reflection about the y-axis. So a reflection about the y-axis means that you're actually rotating the initial ray. So we take this ray, and if we wanted to reflect this ray about the y-axis, we just rotate it 90 degrees this way, and we'll have a reflection of these points. So P and P prime. P prime is the reflection of P about the y-axis, and that's accomplished by rotating P 90 degrees. And the terminal, and the angle for P prime, of course, is 135 degrees as shown. So let's see here. Now, this angle 45 degrees, is called an acute angle. So angles which measure lie between, so if the measure of angle theta is between 0 and 90, then it's called an acute angle. And then if theta is between 90 degrees and 180 degrees, then it's called an obtuse angle. So acute versus obtuse angle. So we can evaluate trigonometric functions at obtuse angles or non-acute angles. So non-acute angles, as opposed to obtuse angles, are angles which measure, with measure greater than 90 degrees. So it includes, non-acute angles, of course, include obtuse angles plus other angles. So non-acute angles are angles with measure greater than 90 degrees. Okay, and so we want to evaluate trigonometric functions at non-acute angles. All right, so let me pull up a technical note. So we want to evaluate trigonometric functions at non-acute angles. And it has to do with what are called the reference angles, which is similar to the reference number. Okay. So we need to define what a reference angle is. So let theta be the angle in standard position. The reference angle, theta bar, associated with theta, is the acute angle formed by the terminal side of theta and the x-axis. Okay? And it's positive. All right, so the do we take it to be positive? It doesn't say anything about the sign, so the reference angle associated with it is the acute angle. Okay, so it's an acute angle, and ostensibly this acute angle could have a negative sign. Okay, well no, we said acute angles are angles with measure between 0 and 90 degrees, so that being the case, then it has to be positive. So we'll take acute angles to be, we'll take reference angles to be any angle which measures between 0 and 90 degrees. So therefore, it will be a positive quantity. So in this case, for instance, the first illustration here, we have theta shown. And so the reference angle for theta is just, that is theta bar. So theta bar and theta are the same since we're in the first quadrant, and all angles in the first quadrant are acute angles. Now, in the second illustration, you see the distinction between theta and theta bar. In this case, theta has a terminal side in quadrant 2. So theta bar then is the smaller angle between the terminal side and the x-axis. So theta bar, so the absolute value of theta bar, or theta bar that is, theta bar plus theta, in this case is equal to 180 degrees. Here we have theta, in the third illustration we have theta being an angle with terminal side in the third quadrant, and you can see theta bar is again a positive angle measured between the terminal side and the positive x-axis. So in this case, theta plus theta bar, their sum is not 180 degrees. Their difference is 180 degrees. Okay, so theta minus theta bar is 180. And then in the fourth illustration, of course, we have the terminal side of theta being in the fourth quadrant, okay, and there's theta bar as shown. And so in this case, 360 minus theta bar is equal to theta, right? So how you can orient things. So we have this procedure now for finding the value of trigonometric functions at any angle. Okay, so now we're going to be plugging in angular measures into trigonometric functions. So let me pull up a note for that. So let me paste it in the whiteboard on the next page. So finding trigonometric functions at any angle. All right, so here's the process. Okay, find the reference angle theta bar associated with the angle. All right, we can do that now. Determine the sign of the trigonometric function of, and this should be theta. Sorry, it got truncated. So this should be theta right there. Okay, so determine the sign of the trigonometric function of theta. So in other words, you'll find out which quadrant the terminal side of theta is in, and then based on that quadrant, you'll associate the sign based on the trig function. All right, so the value of the trigonometric function of theta is the same, except possibly for sine, as the value of the trigonometric function for theta bar. The reason why we want to use theta bar into the trig function is because we've already memorized things like what the trig functions are at 0, pi thirds, pi sixths, pi fourths, all the way up to pi halves. So we can calculate, we've got that memorized, and then we just prepend the sign, the appropriate sign, that's SIGN, and we've got the calculation. So for instance, 240 degrees. Suppose we choose to calculate the sine of 240 degrees. So let's see here, where is 240? Let me pull up a circle. Let me draw it. Let's see. So I'll try it again. So here's a circle. Oh, I see. Never mind. Let's delete that circle. Let's try it again. So here's a circle. And we want the sine of 240 degrees. So let me overlay a coordinate axis. So here's my coordinate axis. And we know right here at the point -1, 0, theta is equal to 180 degrees. So 240, oh, okay, and also we know here at the point 0, -1, theta is equal to 270 degrees. So 240 degrees is going to be here. Okay? So this will be 240 degrees. So that means the reference angle, theta bar, now we're doing this problem right here. So that means the reference angle, theta bar, is equal to, 60 degrees. Okay? And since we're in quadrant 3, we know the sine is negative in quadrant 3, so all we have to do is take the sine of the reference angle and negate it. So we've memorized that the sine of 60 degrees from the table that started this, that was introduced in, where was the table introduced? In Lecture 3.2, right? Yeah, in Lecture 3.2, we know that the sine of 60 degrees is the square root of 3 over 2, and then we just negate it, and so this would be the sine of 240 degrees. Now, okay, so let's go on to the next example, the cosine of 495 degrees. Okay, so 495, what is the reference angle for 495 degrees? So 495 is equal to 360 plus, what, 165? 135 degrees, sorry. 135 degrees. All right, so the reference angle for 495 will be the reference angle of 360 plus the reference angle of 135. Okay, so you can do that. So we know the reference angle for 360 degrees is 0. So theta bar for 360 is equal to 0. So we need to find theta bar for 135. So let's see what that would be. Theta bar for 135. So 135 is 90 plus 45. So here's 135 degrees right here. So that means that theta bar is this angle. So theta bar would equal to, so theta bar for this would be 45 degrees. All right. So then we just take the cosine of 45 degrees, which is the square root of 2 over 2, and we know that the sine of the secant of the cosine function, being in quadrant 2, we would have to negate the result. So the cosine, oh, that's cotangent. I beg your pardon. I thought it was cosine. I read it as cosine. No, in this case, the cotangent of the reference angle 45 degrees is 1, but since we're in quadrant 2, the cotangent function is negative, so the output is -1. Okay. Right, so what's next? The sine of 16 pi over 3. So let's tackle that one. All right, so 16 pi over 3. What is the reference angle for 16 pi over 3? Okay, so that would be 16 pi over 3 is equal to what? That would equal to 12 pi over 3 plus 4 pi over 3. The reference angle for, so the reference angle for 16 pi over 3 would equal to the reference angle of 12 pi over 3 plus 4 pi over 3. So why did I select 12 pi over 3? Well, 12 pi over 3 is equal to what? 4 pi. And we know the reference angles for even multiples of pi is 0. So that what I did was I found the nearest even multiple of pi, which summed with another term is equal to 16 pi over 3. Okay, so this is the nearest even multiple of pi that's to 16 pi over 3. Right, and so we know that theta bar for this is equal to 0. And so all we need to do is find the reference angle for 4 pi over 3. So we know right here, at this point right here, this is 3 pi over 3. And what is this? So 3 pi over 3. And this is pi. And this is 1.5 pi right here. So 4/3 is 1 1/3. So 4/3 is going to be somewhere along this arc. 4/3 pi will be somewhere here. So that means that our theta is, our 16 pi over 3 is coterminal with this angle 4 pi over 3. So 16 pi over 3 is coterminal with 4 pi over 3. So that means that if we subtract pi over 3, then 4 pi over 3 will be back to the x-axis. So theta bar then is equal to pi thirds, which is equal to 60 degrees. Pi thirds radians, which equals to 60 degrees. And so the sine of 60 degrees is, again, the square root of 3 over 2, but sine is negative in Q3. So it's, again, it's the negative of the square root of 3 over 2. Okay. So that's the strategy you can develop. Just find the nearest even multiple of pi to 16 pi over 3, which is 4 pi. And then calculate the reference number of the difference between 16 pi over 3 and its nearest even multiple pi. And you'll get that result. All right. And then the secant of negative pi fourths. Okay, so that one's not too bad. That's just, okay, so negative pi fourths, what is the reference angle for negative pi fourths? Okay, so that means we have to go clockwise, and so that's 45 degrees clockwise. Okay, so the reference angle for negative pi fourths, of course, is pi fourths. And so since we're in the fourth quadrant, the secant is positive in the fourth quadrant, and so the secant of pi fourths is 1 over the cosine of pi fourths, which is 2 over the square root of 2. Okay, so this number, that's not right. That should be 2 over the square root of 2. Okay. All right, so evaluating trigonometric functions at any angle. All right, so now we can go on to the next topic, trigonometric identities, which I briefly introduced in Chapter 2. So now we can extend the argument. Trigonometric identities. All right, so let's paste some stuff in here. Okay, so again, here we have our setup, our usual graphical setup. We have angle theta, terminal side of length r, terminal point py, so here's our point P, and we know that x squared, so if we take r equals to 1 in this illustration, so supposing r is equal to 1, we have a right triangle, and x squared plus y squared is equal to 1. But we know that x over r is equal to cosine theta. And if we take r to be 1, we have x is just equal to r cosine theta, which is equal to cosine theta. And since r is equal to 1, cosine theta. Okay, and the same goes for y. Y is equal to sine theta. So substituting sine for y and cosine theta for x, we have this Pythagorean identity. Cosine squared plus sine squared theta is equal to 1. Okay, so let's see what else. Now, if the radius were not 1, okay, say the radius were greater than 1, we know sine theta is y over r, and cosine theta is x over r. So if we sum the squares of these two quantities, we'll have y over r squared plus x over r squared. That's equal to y squared plus x squared over r squared. And we know that x squared plus y squared is equal to r squared. So we'll have that's equal to r squared over r squared, which is equal to 1. So the Pythagorean identity doesn't necessarily have to be restricted to a radius of 1. It can apply to a circle of any radius. That's one subtle point about this proof here. And then, as we did, I think, in Lecture 2, if we divide both sides of this equation I got in the blue box by cosine squared theta, we'll have this identity. If I divide both sides of this equation, the Pythagorean equation, by sine squared of theta, we'll have this identity. And what else? Oh, and then, of course, we can solve for sine theta. Okay, so solving for sine theta here, by just moving cosine squared theta to the right-hand side and then taking the square root of a square. And so we have a function for sine theta. Okay, so knowing this, we can solve some additional problems. So let me paste one into the whiteboard. And you'll see a lot of WebAssign questions like this. Okay, so if the tangent of theta is 2/3 and theta is in the third quadrant, we want to find the cosine of theta. All right. So to answer this question, you first draw a picture, okay, in the XY coordinate system. So here's your y-axis, here's your x-axis. And we say that theta is in quadrant 3. So that means the terminal side of theta is in quadrant 3. All right, so if this is theta, that means we know that the tangent of theta, all right, so here's our radial segment. Okay, say that's some arbitrary radial segment. This is the terminal side of theta right here. And this is the inscribed angle theta. Okay, so this would be what you'll do then is you'll sketch theta. I got it kind of jumbled here now. So first of all, sketch theta as such. Here's theta. And we know theta terminates in the third quadrant. And so then we identify the reference angle for this particular value of theta. Okay, so there's the reference angle. And so for this reference angle right here that I've accentuated, we know that the tangent of this reference angle is the same as the tangent of theta, with the sine included, of course, the secant included. So for this particular reference angle, the tangent of theta is opposite over adjacent. So the length of this segment would be 2, and then the length of this segment would be 3 for the reference angle for theta in quadrant 3. Okay, so that's the process. So now that you have this figured out, you can actually calculate the length of the hypotenuse, which you'll need to calculate for the cosine of theta. So in this case, the hypotenuse would be the square root of 9 plus 4, which is the square root of 13. Okay, so then all you have to do is just take the cosine of this reference angle, and it would be adjacent over hypotenuse, which is 3 over the square root of 13, and then process the sine, knowing that cosine theta is negative in quadrant 3. That's one way of dealing with it. The other way, of course, is to use the trigonometric identity from the previous page, where we had tangent squared theta plus 1 is equal to secant squared theta, and we know that secant theta is 1 over the cosine of theta. So solving for secant theta, by taking square roots of both sides, we have the secant theta is plus or minus the tangent squared of theta plus 1, and we know in quadrant 3, the secant theta, which is 1 over cosine of theta, is less than 0. So therefore, the secant theta is the negative of the square root of tangent squared theta plus 1, and tangent squared is 2/3 squared, so tangent theta is 2/3, so 2/3 squared is 4/9. 4/9 plus 1 is what? 13 over 9. Okay, so we have the negative of the square root of 13 over 9, and then take the reciprocal. So that's another way of dealing with it. So you can use the identity, which is probably the more efficient way of calculating values of trigonometric functions. Okay, so we can do another one. One where we don't have access to an identity. Okay, so one where we'll have to draw a picture. So oftentimes you'll find yourselves having to draw pictures to calculate trigonometric values. So let's see here. So let me copy one and paste it into whiteboard. Okay, so in this problem, let's say we let secant theta equal to 2, and theta is in quadrant 4. Okay, so a quadrantal 4 angle means that the terminal side is here, quadrant 4. Yellow doesn't show up, does it? Okay, let me use a different color. So here's theta. Theta is a quadrant 4 angle. And so remember to calculate the trigonometric function at a particular value theta, you discover or you hunt for its reference angle, and then you evaluate the trig function at its reference angle, and then you add the appropriate sign. Okay, that's the procedure. So if this is theta bar, okay, so the secant of theta bar is 2, and that would be the hypotenuse over adjacent. All right, since we're in quadrant 4. Okay, and so what do we want? We want the cosine of theta, or the cosine of theta. So in this case, the cosine of theta would be the cosine of theta bar with the sine. So cosine of theta would be 1 over the hypotenuse. Okay, and then the sine of theta would be the sine of theta bar with the secant. So that would be opposite. Okay, in this case, we use the Pythagorean theorem to calculate the length of this leg. So opposite, which is the square root of 3 over 2, and then sine, we know sine is negative in quadrant 4. The cosecant of theta would be 1 over the sine of theta, okay? And the tangent theta would be sine of theta over cosine of theta, and the cotangent theta would be cosine of theta over sine theta. So you can get those results. So that's the trick in solving this graphically. Identify the reference angle for the given angle, evaluate the trigonometric function at the reference angle, then use the correct signage, and then you can use the right triangle to solve for any other angles, or you can use an identity to solve those. Okay, so now let's talk about applications, some more significant applications, such as finding areas of triangles. Okay, rather than using the old 1/2 base times height, there are other formulae for finding areas of triangles. So let me paste the note. So areas of triangles. So consider the first illustration shown here. The area of the triangle is 1/2 times the base times the height. Now, if theta is an acute angle, then we can surmise that the height, as shown by the dashed line, is, well, it goes like this. The sine of theta, if theta is acute, is opposite over hypotenuse. And so h is a perpendicular drop from the vertex here to the line here. Okay, and by geometry we know that this perpendicular is unique. So the sine of theta then becomes h over b. We make b essentially becomes a hypotenuse. And then so the h then, the altitude of the triangle, is equal to b sine theta. And then we'll just plug that into the area formula for the area of a triangle. So the area of a triangle then for an acute angle is 1/2 times AB times the sine of the angle between the two sides. Okay, so if you know the measure of the angle between two sides of a triangle, then you can calculate its area in terms of theta. Now, if theta is obtuse, okay, in this case, as shown in this illustration, the height is B times the sine of 180 degrees minus theta. Okay, so that's that angle right there. So what is 180 degrees minus theta? So that would be now 180 degrees minus theta. Okay, for theta, since the reference angle of theta, okay, so basically what we can do is we can calculate the reference angle of 180 degrees minus theta. So what would that be? So let's see here. If we have an obtuse angle, now remember what an obtuse angle is. An obtuse angle has measure less than 180 degrees. Or is that right? Between 90 and 180, right? between 90 and 180 degrees is an obtuse angle. So an obtuse angle is basically a quadrant 2 angle. So if we have an angle like this, okay, that's well, with the terminal side somewhere in quadrant 2, okay, so here's my theta. Then the reference angle for this theta, the theta bar, is this angle. Okay, so that would be 180 minus theta. Okay, so this angle right here is theta bar. Okay, so how can we? So this notation doesn't look quite right. Let me check that in the text. I think there's an error in the notes here. Yeah, I should have a theta bar. So how can we explain this if the angle theta is not is 180 sine of 180 minus b sine theta. The reference angle of theta is the angle 180 minus. Okay, so the book kind of sidestepped a very important note here. The reference angle of theta, yeah, that's true. The reference angle of theta is 180 degrees minus theta. But how do we know that the sine of 180 minus theta is equal to the sine of theta? Let's see here. So the sine of theta, okay, so the sine of theta, okay, so I think I see it now. All right, I think I see it. It's a little bit, it's a very subtle idea here, but since we're in quadrant 2, the terminal side is in quadrant 2 for this angle, so theta is essentially a quadrant 2 angle. To find, and we know that the sine of let's see, sine of theta. It still doesn't. The angular measures still aren't the same though. Let's see, 180 degrees. Okay, so the sine of theta is equal to the sine of its reference angle. So there's a missing step here. There's a missing step. I see. Okay, so this this quantity right here, based on where theta's in Q2. Okay, so theta is a Q2 angle. So since we're in quadrant 2, b sine theta is equal to b times the sine of its reference angle. Okay, but the reference angle is equal to 180 minus theta. Okay, so that's where this comes from. This is the true angle, this is the reference angle, and so we have this result. So that means the height is still b sine theta for an obtuse angle. Okay, so that makes sense now. All right, it's kind of a little bit subtle. So we can take the height then and plug it back into the area formula, and then we get the same result as with an acute angle. Okay, so the area, so the takeaway is the area of a triangle with sides of lengths a and b, and with the included angle theta is area is equal to 1/2 AB times the sine of the included angle. All right. So, and obviously the angle has to be less than 180 degrees because we know that the sum of the measures of the three angles of a triangle equals to 180. Okay. All right. So let's do some exercises here. Some review exercises for this section to close out section 3.3. So let's find some reference angles for some particular angles. Okay, so let's see. Why don't I just paste it in here instead of writing? So let me go to some example problems. Okay, I wonder if I can just paste in here. It doesn't show up when I paste, does it? Kind of washes out. Let's see if it shows up in Paint. Same thing. Okay, so Adobe doesn't have a good print screen capture. Okay, so I'll just do a print screen. So how about these problems? So find the reference angle for 225 degrees. Well, 225 degrees is in what quadrant? That would be less than 270 but greater than 180, so that's a quadrant 3 value. So it would be 225 minus 180, okay? And if you need an assist, just draw a picture. Just draw a picture. Okay, so here's 180 degrees, here's 270 degrees, so 225 is going to be in here. So to get to the x-axis, you have to subtract 180, so it's 45 degrees. So for 450 degrees, that would be 360 plus 90. So 360 plus 90 is 450, so that's basically, okay, so basically, and we know and so you take the sum of these reference numbers, and so the reference number for 360 is 0, or the reference angle for 360 is 0, and the reference angle for 90 is 90. Okay, so for minus 200 degrees, that would be somewhere in quadrant 2, because you go clockwise. So that would be essentially 200 minus 180 degrees to get back to the x-axis, and it's 20 degrees. So remember that the reference angle is always a positive angular measure. So so 200 degrees is here, and so it's deceptive about why we negate at 200. I don't want to have to introduce additional rules, but minus 200 is here. Okay, and so to get back here, you basically have to find this angular measure right here. Okay, and so that would be, one way you could look at it is it would be 160. To get, you could go to 160 right here in this way, and then to get to the x-axis, you just add additional 20 degrees. Or if it's a negative, you can negate the angular measure and subtract 180 if you wish to pursue that method. Okay, for 17 pi over 6, okay, so 17 pi over 6 is, which quadrant does that end up in? That would be 3 pi minus a 6, right? So 3 pi is here, and then you go back pi 6. So here is the terminal side for 17 pi over 6, coterminal side, that is 3 pi minus 17 pi over 6, so that would be pi 6. So for 31 pi over 4, that would be 32 pi over 4 let's see, 31 pi over 4. That would be 32 pi over 4, which is 8 pi, and that should be, yeah, so that would be, yeah, so that would be 8 pi minus 31 pi over 6. So 31 pi over 4 is in the fourth quadrant, okay? And so you would subtract, to get to the x-axis, you would have to go to 31 pi over 6, which is in the fourth quadrant, and then add pi fourths to get to the x-axis. All right, so that's the technique here. Let me see what the book has to say. Doesn't say much, really, about how to deal with negative numbers. So to deal with a negative angular measure, the technique, a possible technique, would be to take, like for instance in part C of this 4C, would be to take the number, negate it, okay, identify which quadrant it's in, and then subtract either a pi or 2 pi, or subtract pi or subtract it from 2 pi. Subtract the number from, yeah, subtract, well, in this case, what you do is you actually negate the number, okay? You don't subtract anything yet. Just negate the number and then find the reference angle for this angle oriented in the counterclockwise direction, okay? So yeah, just negate the angle. So evidently you can negate the angles, and then that would assist you in finding the reference angles. Okay, so for cosine 300, cosine of 660 degrees, well, that's just the cosine of 360 degrees plus 300. And it turns out, as we showed in lecture 2, the cosine function is periodic with respect to 2 pi, which is 360 degrees. So we have, by periodicity, the cosine of 360 plus 300 is simply the cosine of 300. And 300 degrees is in quadrant 4. So to get back to the x-axis, you have to add 60 degrees. So the cosine of 60 degrees is a half. So yeah, so pay attention to these different techniques for finding reference angles. For negative angles, go ahead and negate them first and then find the reference angles using the customary techniques of finding how far finding the terminal side of the positive angle. Okay, find the terminal side of the positive angle and then calculate the reference angle based on where the terminal side of the positive angle is. Okay, so that'll be the technique. Okay. Let's see here. Next. Okay, so in this problem, we want to write, so how about we do this? Express the cotangent theta in terms of sine theta if theta is in quadrant 2. Okay, so cotangent theta is equal to cosine of theta divided by sine of theta. Now, we know that cosine squared theta plus sine squared theta is equal to 1. So that means the sine of theta is equal to plus or minus the square root of 1 minus No, I'm sorry. We need to express cosine theta in terms of sine theta. Sorry, wrong direction. Try it again. So we have the sine squared of theta plus the cosine squared of theta is equal to 1. So now this cosine of theta is equal to plus or minus the square root of 1 minus sine squared of theta. Now, since we're in quadrant 2, cosine theta is less than 0. Okay, cosine theta is negative in quadrant 2. So that means we'll take the negative part of this expression because we're in quadrant 2. So we'll use this piece. And we'll plug it into the expression for cotangent theta. So this would be the negative of the square root of 1 minus sine squared theta all over sine theta. So this is the expression of cotangent theta in terms of sine theta in quadrant 2. All right, so you'll have a bunch of problems like that. All right, so suppose, next problem, suppose I let cosine theta equals to negative 7/12. And theta is an element of, or theta is in quadrant 3. Okay, so what I want to find then is we want to find the value of theta. Okay, so what is theta? Okay, in quadrant 3. All right, so what we can do is something like this. So theta is a quadrant 3 angle, so something like this. Okay. So the reference angle will be here. So this would be theta bar. So we know that the cosine of theta bar is equal to 7/12. The cosine of the reference angle is 7/12. So that would be, so the cosine is the adjacent, okay, the adjacent over the hypotenuse, which is 12. So this would be 12. So the circle has radius of 12. All right. So now we need. So what are we after? So what is this distance right here? Okay. Okay. So this distance is y, and so we know that 49 plus y squared is equal to 144. Okay, so what is this? So y squared is equal to 95, right? So y is equal to plus or minus 95. Since we're in quadrant 3, okay, since we're in quadrant 3, x and y both have to be negative. So the coordinates of this point would be x equals 7, minus 7, and y would have to be negative as well, so the square root of negative 95. So now we've resolved the terminal side of theta. Okay, we resolved the terminal side of the theta, and we know the radius of the circle, and we know the terminal point for the terminal number that determines theta. Okay, so now, so what we want to do is we want to calculate the sine of theta. So the sine of theta then would be opposite over hypotenuse Okay, there's the sine of theta, and if you need convincing, sine squared theta plus cosine squared theta should equal to 1. The tangent of theta would be opposite over adjacent. Okay, so that would be negative square root of 95 over negative 7, okay, which is equal to the square root of 95 over 7. And the cosecant of theta is just 1 over the sine of theta. The secant of theta is just 1 over the cosine of theta. And the cotangent of theta is just 1 over the tangent of theta. So cotangent of theta, just take the reciprocal of the tan theta. Okay, and there you have it. Okay, so that's the procedure for finding this. If the cosine of theta is negative 7/12, then the cosine of the reference angle must equal to 7/12. And since you're in quadrant 3, so you can draw a picture of the reference angle, okay, and then just set the quantities adjacent over hypotenuse to be 7/12 for a right triangle, okay, and then solve for the y value, the opposite side of the triangle, complete the right triangle, okay, knowing that y is negative in the third quadrant, and then use the techniques for calculating the values of the trigonometric angles. All right, so let's do another problem. The last problem is section 3.3. So I'll paste an illustration into whiteboard. So let's do something like this. We want to find the area of the shaded region, which you can see. So it's this area bounded between the circle and this inscribed triangle, and this is the center. So the area of the shaded region is found by subtracting the area of the sector. Okay, this sector right here. See this sector? So we can find the area of a sector. We know the formula for the area of a sector, minus the area of this triangle. Okay, and that would leave the area of the sector. So the area of the sector is 1/2 times the radius of the circle squared times the measure of the subtending angle. So in this case, r is 2, so 1/2 4, and then we convert theta to radians. So theta, the subtending angle, is 120 degrees. So before you find the area of a sector, you've got to convert the subtending angle from degree measure to radian measure. And that's 4 pi over 3 is the area of the sector. Then we can use the area of a triangle based on the sine of this subtending angle. So that would be 1/2 times the length of the included sides times the sine of 120, which is the square root of 3 over 2, which is the square root of 3. So the area of this area of this region right here, okay, that would be 4 pi over 3 minus the square root of 3. Okay, so you can solve those kinds of problems. Okay, so that will be it for section 3.3. So please, you should have by now be starting your WebAssign questions for chapter 3. So I'm hoping that you're well along the way, because we're about more than halfway done now with chapter 3. So you should be making good progress in WebAssign. So that will be it for this lecture. I'll go ahead and stop here for 3.3. If I can find where it is. Okay, here we go.